Okay, folks, let's continue. So for these two problems, um, now we're able to achieve both the steady state performance and overshoot. And you can check using the formulas we have discussed in chapter 4 that the rise time um, obtained under these controllers should also satisfy the demand. So let's look at another example where we'll discuss the PD controller to conclude this section, uh, this lecture. So now let's look at an unstable system. Apparently this you have two poles, one at -1, the other at +1. Since the plant itself is unstable. And our goal is to use now a PD controller to stabilize the system and to achieve certain performance metrics. So the goal is, of course, the closed loop system should be stable, okay, asymptotically stable apparently. And I want the overshoot after I know the system is stable to be less than 5%. And in control language, 5% is 45 degrees. These two complex poles. And the steady state is less than 0.05 when the input is a unit step. So I have several criterion again: stability, transient, and steady state. Now, as I mentioned, I want to do a PD control in this example. And by definition, you should have a P part, proportional part, and D component. We have seen the P controller earlier and also PI controller earlier. Now, what we can directly see is if we calculate the DC gain. The DC gain of this controller is what? Is Kp. Or in other words, the derivative term doesn't contribute to steady state performance. And it's understandable because, in a steady state everything is smooth, it's flat, there's no derivative term involved. So of course, we don't care about the derivative terms in the steady state. And they only become important in transient and also in stability. So the way that we do the controller is first choose Kp to meet steady state performance requirement, and then choose Kd to meet others. Others means stability if it's applicable, transient apparently, and etc. if there are others. Now let's see if this is the case for this particular system. What can we do? Now for steady state performance, if it's Kd, the open loop transfer function will be equal to Kp plus Kds divided by S plus 1, S minus 1. Let's assume eventually the closed loop system will be stable such that I can calculate steady state tracking error. And steady state tracking error will be 1 divided by 1 plus, and from chapter 7 we know what I want to put here is g of 0. G of 0 is the open loop transfer function with S replaced by 0. And what do I have in this case if I plug in the numbers? You find out on top will be Kp. Underneath will be positive 1, negative 1, so minus 1. I want this to be less than 0.05 or less than 1 over 20. So this will be what? Again, we can view this from multiple angles, and we discussed this. And usually the best way, if you're unsure how to proceed, is you may want to consider put a absolute value sign there, and this will tell you 1 minus Kp absolute value should be greater than 20. Right? Since the denominator here is 1 minus Kp. And now it comes to your discussion. Do you want the Kp to be positive? Do you want Kp to be negative? If you assume Kp is positive, this implies that Kp minus 1, when you take the absolute value, has to be greater than 20. Otherwise, there's no way you can achieve that with a positive number. And this will give you Kp greater than 21. Right. Okay, so you can solve this. The other possibility is Kp, less than negative 19, which will give you the negative side. But I want Kp to be a positive number. Now, so Kp is obtained, and this will give me I'll just treat the boundary values such that ES, as the state is tracking out to steady state, is, when you plug that in, negative 0.05. Okay. What does it mean is the steady state output is 0.95. So it's 0.05 less than the reference one. Okay. Since E is defined as R minus Y. Okay. I'm sorry, let me backtrack this. So in this case, Y should be 1.05 instead of 95. So this is the steady state, and it's achieved by using the P component, the PD controller. And if we switch back to the transfer function, we have 21 plus KD times S. This KD is due undetermined. And S plus 1, S minus 1. Right, this is your transfer function. And this give us a dilemma, because when we look at root locus that we discussed earlier, the root locus doesn't look like this. The root locus look like KGH equal to 0, or K times GH over 1 plus GH. This is KGH. This is the form of the transfer function we have seen earlier. Okay? They all look like this, but this doesn't. On top, you don't see that, K in front of everything. So the way to overcome that is to find out the characteristic equation first, because the root locus is trying to solve for the closed loop pulse. Which will be S squared minus 1, okay, and then plus 21 plus KD times S equal to 0. And reorganize the term, we have what? We have S squared plus 20 and plus KD times S. Or we can write it as 1 plus KD times S over S squared plus 20 equals 0. This being the characteristic equation of the closed loop system. Now, if we look at this, if I organize the term in this manner, meaning I put all the terms with KD on one part, in one group, everything one term, and the rest, then this guy looks like something that can be done similar to what we have above. And what you need to do is to view this as your open loop transfer function to sketch the root locus. And when you sketch a root locus, you're still trying to find the root locus for this open loop transfer function, or for the system that we started at the first place. Still this one. But it now looks a little slightly different. Okay. And when we do the do this, we can find out that you have 1 0 here, and you have a pair of complex poles, one here and one here. And how do we study such a system? Well, the way we look at this is, again, using the same method we discussed before. You have two poles of two branches. You have one pole, 1 0, so this is one ending point. The other ending point has to be at infinity. And since the order difference is 1, 2 minus 1 is 1, that asymptote should be extended to 180 degrees, so left hand side of your real axis. Okay? And you don't even have to count the central. The central has to be on the real axis. What other can be done is find the segments of the on the real axis on the root locus, and this entire part will be up. Okay? This entire part will be part of it. And what you are doing is you are connecting a 0 with infinity on this row locus. And here you have a pair of pure imaginary poles. And what you should expect is the direction to go this. There should be a break in at a certain point. I don't know where, but there has to be a break in. And what you can do is connect this branches from the poles. You connect the branches from the poles. And this is what we have. Now, one interesting thing is, see, the two poles here are actually what? This is actually j square root of 20, or is actually j square root of, believe or not, kp minus 1. Okay? If you see, this 20 actually comes from 21, this is your kp, minus 1, so actually this. Now, what it means is, if you have kp selected at 21 to achieve this 5% error, this is what you achieve. If you are going to choose a larger kp, you are looking at the root locus like this. Sorry. You're looking at the root locus like that. This is a larger kp, meaning smaller steady state tracking error. Now, what other things do I need? I need stability. Is that a problem? Now, if I draw the root locus correctly, that won't be a problem because all the roots are on the left half plane. What others? I want also an overshoot being 5%. Well, how do I find the overshoot being 5%. This is what I did, right? I find this 45 degrees. I find this intersection here, this intersection here, or if a larger KP will be here and here. And now I can plug in the rules in order to find the KD involved. And then from there I can figure out the parameter of the transfer function. The parameter of the controller that I'm using to design it. And that will satisfy both stability, right? It's on the left hand side is check. Steady state tracking error is guaranteed by how you choose the position of the KP. And the transient, well, preliminarily it can be satisfied as long as I choose the points along this 45-degree angle curve. And again, as I mentioned, when everything's done, our entire discussion in chapter 4 is by looking at a system that has no zeros in the denominator, no zeros in the closed loop transfer function, and only a pair of poles in the denominator of the transfer function, meaning a quadratic system, second order system. But in this particular system, you will have a finite zero, so you want to be careful. Although this is how you choose your system, you want to plug in the system into MATLAB Simulink and do a simulation and quantitatively evaluate the overshoot. If it satisfies the 5%, then you're good. If not, then you have to tune the parameters, maybe move it down a little bit, add a little more damping, such that you will be able to have less overshoot in that case. And that will be the methodology. So for this particular system, I want to leave it as an exercise, which you can try and see if you're able to find a P controller or a PI controller that will render the system to be asymptotic stable, have the desired transient performance and steady state performance. Okay? And on Tuesday, when we meet again on Tuesday, we'll use that as the starting example to discuss, to revisit this example and see whether or not we can use P and PI controller to stabilize it. Okay? And after that, we'll discuss how to combine all three, meaning we'll design PID controllers. And after that is done, we'll wrap up the root locus chapter and move on to the frequency domain control design material. Okay, so this is the end of this lecture.